All right, let's get started. Today we're going to continue talking about power flow and actually talk about how you solve these power flow equations. I'll provide a brief review before we get started with that, but that's going to be the majority of the class today. One important note is that please do get the latest, sorry about this, but please do get the latest slides that were put up this morning. I put a little note. If you downloaded them, when you saw a little note saying updated today, use those. It's a little swap of variables. I had flipped variables in theta I minus theta k instead of theta k minus theta I, or vice versa rather. If you have the old notes, you can still use them. Certainly, it's just one little problem on them, but it is a mathematical formula, and it is different. So just please get the latest one. It was just a typo on that, but it was throughout all of them actually, because I was copying those. So please get the latest slides, and we'll in fact just derive. In fact, you'll see why the equations you'll see today are the right ones. But if you don't have that, and if these look different at all here, if you didn't download them when it says a little updated bold in bold on the website, updated today, then just get the latest ones. But if you printed out the old ones, it's fine. Just correct it. Make a note of correcting it when you see that. So the other thing is the homework is due tomorrow, or sorry, Thursday rather. Homeworks will be due at the beginning of class, and you do have those late days if you haven't used them up already. But do try to get it in as fast as possible, so you can save those for more important things later on. Were there any questions? And the other thing is that we're going to have those extra office hours tomorrow from I think 2:30 to 3, 2:30 to 4 rather. So extra office hours because of the homework being due. Do stop by if you have any questions. I didn't get that many people yet, so I assume that means you're all already done, or I'll be optimistic at least. All right, so today we're going to keep talking about power flow. And to highlight what we did last time, remember, the basic idea was we want to know from a bunch of generators and a bunch of loads how current and how power will flow in the network. And the tricky part here was that we can't easily know all the voltages and currents, at least not the absolute voltages and not the complex voltages and complex currents. And so it's hard to solve this system like a linear equation, as we typically did in linear circuit analysis. And so because of this, we can still write down the equations governing the system by substituting in our expressions for how voltage and current relate to each other. But what we get in the end is now a nonlinear set of equations. And so we're going to solve those with Newton's method. Now remember, there are also all sorts of little specifics here. The variables we're interested in is power, which include complex power, which include the real power and the reactive power. And then voltage, again, complex voltage is our other set of variables that include, we're going to write this in terms of the polar form that has the absolute voltage magnitudes and then these thetas, which are called voltage angles. And these are the sets of variables. These 4 variables, one for each bus, for each node in the network. We'll call those buses. Those are the variables that we want to find. And there are 4n of these, where n is the number of buses, because there are 4 variables, relating power and voltage here. And for each bus, we know 2 of these, and we don't know the other 2. And in the end, we're going to have, so we have 2n unknowns, 2n knowns, and we're going to end up having also 2n equations, so that we can use these 2n equations to solve for the 2n equalities. So we can use these equalities to solve for the unknown variables. Remember, buses came in 3 different types. There was the slack generator, which is the one that has to sort of pump in the extra power. Again, this does not really correspond to a physical thing when you actually run these in the real world. But for the purpose of solving these equations, we can't really know the total power that this slack generator would generate beforehand, because it has to provide the power for the losses in the network. And so we actually assume we know the voltage magnitude. We can control that with most generators. We're going to assume we know the phase angle or the voltage angle, which is going to be referenced to 0. And we're going to find real and reactive power. That's for one generator called the slack generator. For most generators, called PV generators, well, for most generators, you can control how much power they output, right? That's just sort of how hard you push on your crank. You can control their voltage by essentially putting more or less current through that electromagnet in the rotor of these generators. And what we're going to find then is what are the resulting voltage angles and reactive powers. And finally, for loads, we're going to assume that the real and reactive power are known. That's kind of what a load does, where it just consumes some amount of real power and some amount of reactive power. And we're going to find the other two ones, the absolute voltage magnitude and the phase and the voltage angle. Now, as I said before, power flow is really just expressed as this one equation here. And it's important to remember, so diag here constructs a diagonal matrix with those elements on the diagonal. That's essentially a way of multiplying the entries of this vector piecewise with this thing, or element by element with this thing. So if you haven't seen it before, do make sure that you get that point, because it's just sort of a little notational thing here, but it is important to understand that equation. This is a set of equations. It's really a set of n different equations, but there's both a real and an imaginary part to it. So it's really 2n equations, because the real portions have to be equal for both these things, and the imaginary portions have to be equal for both those things. And this, despite the form you might see, and you will see later in these slides, people typically write a lot more complicated than this, but this is power flow here, just solving this equation. That's all it is. So keep in mind that we're doing something actually that's not that complex here. Just solving that equation, basically finding a 0 of this minus that, if you want to think it more in terms of Newton's method. Now, Now, as a little sort of aside, because we haven't really talked about this much, I wanted to mention that for networks like this, so we had this sort of 3-bus example here. I'll go back several slides. Sorry for flipping back through. For buses like this, where you have buses that are hooked up to generators or loads, or potentially both, we'll see in the future too. You have buses that are essentially just nodes in that network. They're connected, and they assume you have 0 resistance between those. So if you had a load and a generator on one, you would assume there was 0 resistance between it, and 0 impedance. And then if you assume a pretty simple model for these transmission lines, it's actually quite easy to write down what this Y matrix here is, what the admittance matrix is. Remember, we started out talking about circuits in general just by saying that the current was related to the voltage by this matrix Y, which is known as the admittance matrix. And I sort of waved my hands in terms of how you actually solve it. I said computers can form this easily, so we're not going to worry about that. Quark solves it. But it turns out actually for power systems, these kind of simple networks where you sort of know where your reference points are, and those are the buses, it's actually pretty easy just to form this matrix. And so I'll just write what it is. I won't derive why it has that form, but I'll write what the form is just so you know the form and you know it's actually fairly simple to go ahead and compute. So we're going to let Ri be the resistance between nodes I and nodes J. And if there's no wire between them, that would be infinite. Right? We're also going to let Xij be the reactance. Remember, reactance is the imaginary portion of impedance. So I forget what Zij, that's the impedance between these two things. Remember, it equals something like it's the resistance between those two plus j omega times the inductance between them minus 1 over omega times the capacitance between them. But we're going to, this whole thing here is just called xij, which is called the reactance. I think I might have mentioned these terms before, but you have a lot of terms here, right? You have capacitance, resistance, reactance, impedance. So just the xij is just the whole complex term of impedance, and that was just what we call reactance. So given these two things, then our admittance matrix actually has a very nice form. All it is the following. It's a symmetric matrix where the ith element for non-diagonal elements is just 1 over the impedance. And I could just write this as the total impedance here. I'm separating it out into these two things, so it'll actually be nice to think of it later on as some of these things being 0, some of them being positive number. But this is a definition. So off-diagonal elements of this Y matrix are just equal to the negation of 1 over the impedance. Right? And the diagonal elements are just equal to the sum of all the inverses of the impedances. So you basically take all your off-diagonal elements here, negate them, and sum them all up, and that's diagonal. That's the entries on the diagonal. So we're not going to quite derive why this is the case. I mean, essentially it comes out just from Ohm's law and from very simple applications of Kirchhoff's voltage law and current law. But this gives you the form of this admittance matrix that you can use to actually solve this. So now you actually know not just, theoretically how to solve these things, but for an actual network where you know the resistances and the reactances, you would know what these things actually, how to actually compute these elements here. Now, there's one important point which makes this a very nice matrix to work with. And so suppose we don't have a line between nodes I and j, right? What would the value of yij be then? Yeah. So then we get that if you have no line, the resistance is infinite. And so 1 over something really big, well, that's 0. The reason why this is nice is when you have matrices with a lot of zeros in them. These are called sparse matrices. And you can often compute a lot of things, like you can you can multiply by the inverse of a sparse matrix much more efficiently than you could if it was a matrix of all non-zero elements. Sorry, not positive, of all just non-zero elements. And this kind of makes sense, right? So think about just multiplying this product here, right? When these guys don't have many non-zero entries. Well, basically, when you compute your matrix vector product, a lot of those terms are just going to be 0. And you can know kind of beforehand which ones are going to be 0 by just looking at the sparsity pattern here. So you actually can really simplify the computations a lot for something like this product here. Now that same thing holds for multiplying by the inverse of this. Ignore for the moment, this is actually not an invertible matrix. You'll actually prove something like that on the next homework. But for a sparse matrix in general that is invertible, you can often multiply by the inverse of it much more efficiently than actually going through the steps of inverting the matrix and computing that inverse explicitly. And this is actually another sort of nicety of MATLAB, in that when you use that backslash operator, so say you have A backslash B. I'm just using generic MATLAB code here. These are not related to any of these other A's or B's or whatever. If A is sparse, MATLAB will automatically compute this more efficiently than actually this. Inverse of A times B. So this is especially when A is sparse. It's actually true regardless of whether A is sparse or not. And you can do this by just doing quick timing tests on your own, for 1,000 by 1,000 and 2,000 by 2,000 matrices here. What you'll find is that this one is much faster. This is especially true for sparse matrices. We won't get into the algorithms of why this is true, but it's sort of similar to how you can efficiently multiply by sparse matrices. The thing you do to solve these systems, which relate to factoring these matrices in kind of interesting ways, those are also more efficient for sparse matrices. So the fact that Y here is sparse is very nice. And by the way, that's why we work with this form here, right? We also knew, so from similar equations, you could also write this like this, that the voltage equals some matrix, some impedance matrix, times the currents. It's not quite the inverse, because again, these are not invertible, but both these relationships do hold for certain matrices here. We could have done everything in terms of this. So taken our voltage, one of our voltages, and plugged in current and had two terms that relate to current. The problem is this matrix is not, the impedance matrix here, is not sparse. And that's why we end up working typically with the admittance matrix for all these equations instead of the impedance matrix. And now you know how to compute the admittance matrix, so you can compute all these things, all these relevant equations. So I'll just erase this because we don't even want to think about something as nasty as that. Yeah?
So it's only sparse when there is no transmission?
Right, yes. So it's 0 when there's no line between two different nodes. But this is actually not uncommon, right? Think about every single generator and every single distribution bus in the power grid. They do not have a dense set of transmission lines connecting every one to every single other one. It is a very, very sparse grid, the power grid, right? I mean, just think about, you have like I'll just draw a quick example. This is not what the power grid actually looks like, but say you had some network like this, just a grid, and you say you take the sort of intuitive thing here and just draw lines between all of them. Done that more efficiently, drawing those lines there. So this is it's still not. It's still sort of a robust network, and if you take out one line, there still are paths between other things. If you knock out too many, there may not be any more. But it still there's a reasonable amount of paths between each node here. You sort of think of this as a nice network. But think about how many fewer lines there are here, connections there are here, than it would be if you had a dense graph. So if you had a dense graph where everything was connected, and so that admittance matrix was actually dense, you'd have to be having transmission lines between all of these things, right? So you'd have this. It's just for one node. You'd have that same thing for every other node, too. So it's a huge difference here between the number of nodes you would expect in a network that's kind of laid out geographically and maybe has the sort of intuitive connections between nodes in the network that are kind of close together geographically, and one that would be densely connected. That's just completely infeasible to build a grid where this would be a dense matrix in general for a big system. And they're often very, very sparse. I mean, oftentimes, they're actually, each node typically has approximately, you can think of it as having a constant number of connections coming out of it. And so if you had a fully connected graph, the number of nodes would grow, the number of connections would grow like n squared. Whereas if you have a graph like this, for example, at most each node has 4 connections, right? A grid network like that. Now again, that's not what it really looks like, but there is a huge difference between n squared and 4n for large n, right? So the sparsity plays a really big role here. Okay. So now let's get to the meat of power flow itself. And how do we actually go about solving this? Oops, did I? Okay. So I'm going to write down the nasty equations that you'll see if you ever read a paper on power flow. Everyone writes it this way instead of, I don't even write it here, but this is power flow, this equation right here. No, not many characters here. So is this. And everyone, for some reason, chooses to write it this way. It's just, I mean, it's notational. There's a little bit more information carried here. You see the actual phase angles more explicitly here. But it can be confusing. These equations look kind of daunting here, but they're really just the exact same thing as the equation before. So the way you get to here from here to the one in the previous slide to here is just algebra. So I'll just write out this kind of expression here because you should be used to seeing it. And what this does is this actually writes out what these equations are in terms of the individual components of real and reactive power, and in terms of the individual voltage magnitudes and voltage angles. That's just how people often write power flow. When we actually go to solve it, though, it'll be much nicer to go back to the old form, just for sort of reasons of computing these derivatives, everything like that. You can imagine the Jacobians here get pretty nasty. Though plenty of people do write them this way, or in a way like this, which is just horrendous. So let's talk about why this holds. It's good to just sort of go through this derivation pretty quickly. It's actually pretty straightforward. It's, again, just algebra. So remember, our equations were S equals diag V times Y conjugate V conjugate. Where the conjugates there are taken element-wise. It's not conjugate transpose, it's just conjugate. Take every element in the matrix and conjugate it. So let's look at a single element of this guy here. Well, this is equal to just this term. So, and I'll even write the real and reactive portions independently. So I'll look at PI. Apologies, I'm going to use I again, even though I sometimes means current here. We won't deal with current at all in these next several slides, so I'm going to start using I because it gets sort of nasty to run out of indices otherwise. So we're going to say the power, which has a real and reactive component, is equal to, well, this first voltage there, VI, times, I guess I'll write it out term by term, the sum from I equals 1 to n, so k equals 1 to n. K equals 1 to n. You know, this is actually, I'm going to write this a little bigger. It might be hard to see in the video. So, the sum from k equals 1 to n of y conjugate I k. I actually can do it either way, but I think I want to write it that way. V conjugate k. All right, and now we can also substitute in now the complex form for all these things. And so we're going to define y. I mean, remember, y is this admittance matrix. We defined it in a certain way, but we can also just write it in terms of its real and imaginary components. So we're going to write y equals g plus jb. These each have names too, and I actually cannot remember what they are right now. There are more names like impedances and reactances. I think one's susceptance, and I can't remember the other one. I'll put those in the notes or mention it next time. But it doesn't really matter. We're just going to separate it like this, and this is the common notation: G for the real part and B for the imaginary part of y. It's important to know that, remember, yij equals 1 for I not being equal to j equals -1 over rij plus jx. Boy, I really screwed that up because now I'm using j twice here, but I'll use k here, even though I guess I validated this in the notes even. So yik equals rik jxik. But it's important to note that g in general does not just equal -1 over r ik here, and b does not equal -1 over j xi. you have to do the actual complex inversion here. And you get a new complex number with a real imaginary component that correspond to this. But it's not like you can do it element-wise. So just keep that in mind. Y itself is going to have a real and an imaginary component. And now we can just write out these voltages, for example, in our rectangular form here. Write out Y in the rectangular form in terms of the G and B matrices. And we're taking the conjugates here, so we're going to subtract these things instead of adding them. It's actually easier to work with the voltages, though, actually still in polar form. It'll make our life a little bit easier. So let me just write what this thing is equal to using this form here, but then using the exponential form for the voltages. So this equals V hat I. Remember, V hat I is the absolute magnitude of the ith voltage times e to the j theta I. That's our way of expressing complex numbers in exponential form, times the sum from k equals 1 to n of, I'll write this out now, I suppose, g I j, sorry, g I k plus minus j b I k times the magnitude of the voltage at node k times e to the negative j theta k. And that negation comes in here because we're taking the conjugate of v. So the nice thing about this polar form here is that it's actually easy to multiply complex numbers. You just add their exponents and you multiply their absolute magnitudes. So this is why we wrote it like this. It's a little bit harder. I mean, you'll get the same thing here. What you get if you do this is you get terms that have cosine ik times cosine theta I times cosine theta k. And you can use things called the, the trigonometric identities called the double angle formulas, or the not double angle, I guess, but identities for adding and subtracting angles in a cosine to convert this one to the other. But it's much easier if you just do it in this form here. I mean, they're all equivalent, of course, but this is just sort of an easy way of showing that. So this is equal to, we'll leave this guy out here still, just because this is the constant for all terms in the sum here, right? It doesn't depend on k at all. And we'll push this term into here. So this equals v hat I times k, the sum of k equals 1 to n, g I k minus j b I k times times v hat k e to the negative, I'll write it like this, e to the j theta I minus theta k. And by the way, if you print out your notes, this is what I mentioned before. I had originally just had a typo and swapped the order of these things in the notes. So please do get the last one, or just correct it in your notes if you printed them out already. It's theta I minus theta k. So now, let's go ahead and write this back in kind of the rectangular form and multiply these things out. Actually, I'll just write it like this at first, because I don't want to write all this again, but this is equal to v hat k times cosine of theta I minus theta k plus j times the sine theta I minus theta k. Okay, so this is now saying, remember still, the real and reactive component here is equal to this whole thing. And this equation here obviously has some imaginary numbers and some real numbers. And so we're just going to write separate equations. We're going to look at this whole thing, look at the real component of it, and that has to be equal to the real power. We're going to look at the imaginary component of that, and that has to be equal to the reactive power. So whatever terms in this have a j in front of them, that'll be the reactive power. Whatever terms don't have a j, that'll be the real power. And I'll just do the real power here. So when you multiply, so there's a product here, and actually this isn't great because let me just write this all out with more space. So equals v hat I times the sum from k equals 1 to n gik minus j vik times v hat k times the cosine of theta I minus theta k plus j times the sine of theta I minus theta k. That's it, right? Put the parentheses around these things too. Okay, so now let's multiply this out and look at only the real portions. Well, there's the imaginary number here and one here. So when you multiply these, so the real component is going to be these things. And then also when you multiply j times j, those are going to cancel to become -1, and you'll have a real portion again. So the real portion here is equal to, so pi is equal to vi times the sum from k equals 1 to n of, well, the first term we'll get is just this times that. That's still real. Gik cosine theta I minus theta k. Next, we have minus b something and then plus something else here. When we multiply the j's together, though, those create -1. So we have plus bik times the sine of theta I minus theta k. Now, the point of all of this was just to show you that, in fact, this equation here is just an abbreviated way of saying this. Right? This is the exact same thing, these two equations here. This is just writing out explicitly in terms of both the matrix product and in terms of this polar form for voltage. This is just writing it out term by term, what those things are. And that, if you read a book on power flow, you will see these equations, not this one. Not this one, usually. I'm not sure why. I guess it's just a more explicit form, and people have gotten used to that. Yeah?
Clarification, what's the difference between the I and K?
So the I is the index of the power here. This is actually really very important. The I is saying the power at the ith node is equal to this thing. K is what we're summing over. So we're summing over all k's. This is an equation where k is the variable that sums over all nodes from k equals 1 to n.
So k also represents the nodes as well?
K indexes over nodes. Yeah, there are n different buses in the system, and k sums over all of them. So what this says is the power at the ith node depends on the voltages at all the other nodes. Now, not quite, because these terms are all 0 when the nodes are not connected. So directly, in terms of this equation, what this says is really the power equals the voltage at the current node and then some function of all the other nodes that are also connected. Now, because every other node also has those properties, you really get the dependence between all the different voltages and currents on each other. They all have to sort of be assigned correctly in order to make these equations be satisfied for all I. But what this is saying directly is that the power at the ith node depends not just on the voltage, say, at the ith node, but also on the nodes that are connected to that node. And that's what this sum is saying here. All right, so now we have the equations. So now let's talk conceptually about how we go about solving this. Remember, we have two equations for each node, and we have those two n, so we have two n equations, and we have those two n unknowns. So here's conceptually what we can do. We can write let z, and this is just for an example here. We're actually going to later put z in a form which is more manageable, but this is just sort of conceptually what we're doing. We can write z as a vector of all the things we don't know in our network. Okay, so for the slack generator, we know the voltage magnitude and the voltage angle. So what we don't know are the real and reactive power. For the PV generators, however many of them are, what we know is the voltage magnitude and we know the real power. So what we don't know, again, is the reactive power and the voltage angle. And then finally, for PQ loads, what we don't know is the voltage and the phase angle. Don't worry about these sort of indices here. I'm just making it so they all add up to the right number of items in a vector here. They're actually kind of even a little bit confusing. But the basic idea is we're just lumping all these things into this big vector. But ultimately, we'll do it in a different form anyway. I'm just trying to say kind of conceptually what we can do to solve this with Newton's method. And then, and I actually really should have swapped these things. So, OK, actually, I'll say it now, but it will also maybe change this in the notes too. Then we can let g be a function. There's essentially the error here. G is this thing minus that. So if that is equal to 0, remember, Newton's method finds zeros of a function. We're going to find some setting of our unknown variables such that some function is 0. And that function is just the difference here. I wrote this right now in terms of the powers minus the other side of the powers. But really, actually, for the most part, I'm going to have it be the other way around. So it'll actually be this thing minus that thing. Of course, they're both equivalent. One's just the opposite of the other. But when they're 0, this minus that is 0. And so is that minus that, because they're equal. But just, again, just sort of conceptually, we have our unknowns. We have our power flow equations. We can just write out a list of all those those 200 power flow equations. They are functions of our unknown variables. And we now have a function, g of z, this is a vector valued function. It's important to remember. So that g of z takes as input these 2n unknowns and produces 2n values that encode these differences here. So we can apply Newton's method to find a 0 of this function. Through the updates, z is set equal to the Jacobian of this thing, g of z, inverse times g of z. Sorry, z minus that. Z goes to z minus this.
So g of z equals 0 implies
These things are all equal, and that is just the power flow equalities. In the rest of the lecture, I'm actually going to have these flipped, so I'm going to talk about this minus that. So don't worry about the actual form here. This is not the actual form of z that we're going to use, and it's not the form of the function that we're actually going to use. But conceptually, this is what's going on. Okay, we're actually going to go back to our older form of the vector form. It makes things much, much easier. But let's just think conceptually we can do this. And really, a lot of power flow books describing power flow, will do this exactly. And say, OK, now we have 2n equations. We have 2n unknowns, all these variables here. Let's just compute the derivative of every single one of these with respect to every single one of the other things. And those let us compute the Jacobians. And as you can imagine, this gets really tedious really quickly. So, right, you have real and reactive power terms here. I have a few, I think, on this next page. So you have you have real power terms and you have reactive power terms that have to be equal to each other. You have unknown variables that include voltage angles, voltage angles, voltage magnitudes. You have power, real and reactive power too. Those actual derivatives are pretty easy because those are just, you only have sort of a linear term here. That would just be 1. They even leave those out of the books. But you also have the voltage, the derivative of this guy, the ith power flow equation, with respect to theta I, and with respect to theta k for k not equal to I. So those are actually different derivatives here. You have to do these differently depending on which thing you're differentiating with respect to. And you actually need 8 of these total. And they look about as hairy as this. And I think when I was computing these, I made some mistakes. I had to go and check a book to make sure I was getting it right. I've seen books that get these wrong. They're really actually quite cumbersome to write out. So that's kind of a pain. Yet it's actually how people describe power flow in a lot of cases. This is power flow. You compute those Jacobians. And that really misses the whole point that you're losing things like the sparsity here. I mean, I guess you have some sparsity because you can only sum over the things that have the individual elements. But you're really kind of missing the overall form of this when you talk about writing these things out term by term. So again, you probably will see this if you read a book on power flow. But I'm going to show you an easier way of doing this. So instead, we're actually going to think of z in a slightly different form. Let's take a z that includes all the variables that we know about. Okay? It's going to include voltage angles, voltage magnitudes, real powers, reactive powers, all in a big vector. Sort of a much nicer form than kind of this other convoluted form of z I showed you before. So z is now a vector in r to the 4n, where some of those are known and some of those are not known. Okay, so z, first of all, bring out of ink here. Z is a vector in R 4n. Is equal to all these things. Just equals angles, voltage magnitudes, power, real power, reactive power. And these are vectors of all these things, right? So it's a vector of all the different voltages, all the voltage angles, all the different voltage magnitudes, all the different real powers, all the different reactive powers. G, I'm going to define as a function of z, which is just equal to the real and imaginary portions of this difference in that order. Remember, we don't want to write these equations in terms of their actual imaginary components. That's a little bit nastier. We still want to look, Newton's method is a little trickier in that case. We're actually going to write them in terms of the actual voltage angles. We're still going to write out the different components of our imaginary numbers here. We're just going to do it in a way that sort of, in computing them, we convert them to imaginary form and then basically compute them back to get the numbers here. But these are all real valued numbers here, so the important thing. So g, which in this case is a function that goes from this r4n to r2n, that's going to just be equal to g of z equals the real and imaginary portions of this difference. So remember, our equation basically is diag v y v minus s, and we'll have the real portion of this and the imaginary portion of this as our definition for G. Yeah?
Wait, can you say again why it's better to do it this way? Why not use the complex form?
It's just, yeah, you actually could do it that way too. The thing is, you typically actually want in the end to get, well, so there's a few reasons actually. The real reason is that things like power, it's easier to set what you know in some sense in this form. So what you know is you know some voltage angles, for example. Right? If you write out a number in complex form, then you say, okay, my number would be, say, internally you have to do this in the computation too, if not in the actual writing of this. Internally, it would have to have some representation like this, numerically, right? Now, we know voltage magnitude here, but we don't know the actual angle. That's what we don't know. And what that is actually is a constraint that says, well, we know the absolute value of this thing, right? We know a squared plus b squared, but we don't know the other values. So this actually becomes much trickier to write the constraints out like this that actually say what we know and what we don't know than it would be if you when you write them out all explicitly.
It just corresponds better to like how you formulate the problem.
Exactly. I mean, but more than that, it corresponds to what we actually know about the problem. We don't know the real and imaginary portions of voltage. What we know just from physical properties is we know the magnitude of voltage. And because of that, we really have to write it out this way. We can't really talk about, because numerically, Newton's method is just doing sort of the same thing. It's just doing Newton's method on the numerical real and imaginary parts of it. And that's not what we know in power flow. So it's much easier. I mean, it's really only possible to kind of specify what you know here when you're doing it in this form like that. You can also actually run Newton's method with the original sort of rectangular form for everything, and then add those nonlinear constraints that say this squared plus that squared equals something else. That can oftentimes be a little more cumbersome, though. It just isn't quite as nice as this. These terms all end up being very nice here. All right. So we have these definitions. Now I'm just going to say what this is. If we get these definitions like this, if we define everything like this, then the Jacobian with respect to z of g of z equals this thing. Some real portion of the sum matrix J1. I'm calling this J. J is often the sort of shorthand for Jacobian, but it's just the Jacobian here. The real portion of some matrix J1, the real portion of some matrix J2, these are kind of obvious, right? Because sort of the Jacobian with respect to this first bit of the real power, well, obviously that's sort of just going to be negative I because it just depends on that. The other one is going to be, and doesn't have any reactive power here in the first block. And then the Jacobian of the reactive with respect to the reactive power is going to have a negative identity there, and et cetera. So this block's kind of easy here. This one's kind of the tricky one here, what's going on here. And I'm not going to actually derive this, but it's actually really simple to do this. And it kind of intuitively, this just looks like normal differentiation with the chain rule. And you actually can derive this all by applying these same things, just using the chain rule. So just to give you some kind of sort of brief intuition of why this might be the case. Let's see if I can actually get all these things right, because I'll make some mistakes too when I start doing complex matrix differentiation. But basically, so you have a term that looks like this, right? And so essentially, let's look at this term. The real part of actually let's just look at, because if you'll notice, this actually just looks at real and imaginary here, just like this is real and imaginary here. Let's just think of it in terms of taking the overall Jacobian. I'm being very hand-wavy here, but again, you're not supposed to know how these come about. Just know that these do, in fact, come about. This is the definitions here. So you have some term like diag v, y star v star minus s. Let's take the derivative with respect to, say, theta. So let's write v, diag v as v hat e to the j theta, y star. And this is, so we're doing this sort of element-wise here. Don't worry about the details exactly. But I'm being very kind of informal. And then we have v hat e negative j theta. So I mean, again, this is not very rigorous here, because these are sort of multiplying piece by piece here. Then we're talking about element by element here. Then we're taking diagonal matrix, but just ignore that for the time being. So let's look at sort of theta. Well, theta, when we take the derivative with respect to theta, what you get out is you get out Well, you'll get out like a theta in front there. So you get, just make sure I'm getting this right. Yeah, so you get out something that actually looks like this, right? Because you have a theta comes out here, and so you have, rather a j comes out here. That's the term that multiplies theta here. So you'll have a j that comes out front. You'll have this term diag v e j theta, and then you'll have this term as before v hat e negative j theta. You'll also have a and this kind of looks like this part here, rather, this part here. Yes. You have j come out the front. You have this diag v. Right, sorry. You actually have diag of this. So diag of this thing, just by the product rule, how this works. And again, I'm being very, very hand-wavy here. And then you also have something like this. Looks like, well, this you'd have also just diag v times the derivative of this thing, which you get another j to pop out. And that kind of looks like this term here. So if you want to go through this all, you're welcome to. You can look up the chain rule for Jacobians, but you don't need to. The point is just that these things follow from the chain rules. And the overall point is really that this is much easier to derive than each of those individual Jacobians piece by piece. They're, of course, equivalent. I mean, they're, of course, equivalent. If you look at what each element of this matrix is here, you get the term by term Jacobians and write out the whole term as you do with the other ones. You get something like this here. This is not even worth really writing down here. But you get something that is, of course, the same as this. But the nice part here is that these all terms are all really easy to actually just write in MATLAB, right? I mean, this is all just some diag terms, etc. And the interesting thing here, the really, really nice thing is that the sparsity patterns of these two matrices are the same as the sparsity pattern of y. And that you can see pretty easily, right? Because what you have is you have y times diag v. That just scales the rows of y, so the columns of y. You have a diagonal matrix here. This is going to be diagonal, and every element in the matrix does have a diagonal entry, so it does not change the sparsity pattern. And then you pre-multiply by another diagonal matrix here, which just scales the rows. Right? Same here. You have y times diagonal matrix, and then two diagonal matrices times each other here. So all these terms have the same sparsity pattern as y. And so in Newton's method, remember, we're multiplying by the inverse of these Jacobians, but they have the same sparsity. So if y is sparse, they will be sparse too. And that makes things very nice for us, because we can use all these kind of nice solvers for sparse matrices. Incidentally, would anyone actually really like to see me, I can't do it this time because I have to look up those rules. Would anyone like to see these actually written out, just by a quick show of hands? OK, one person, so I can just tell you later. It is just the chain rule, but again, I don't clearly even remember how to quite do how these rules all apply when you have diagonal matrices multiplied by other matrices, etc. But that's really all it is. It's just a bunch of chain rule applications with matrix algebra. Sorry, matrix calculus. Yeah.
So J1 and J2 are just...
I'm just defining them. They're just defined as this.
Okay. Jacobians.
They're not really Jacobians themselves. Yes, they are a Jacobian themselves. They are with respect to one part of this, so it's a one entry, the theta entry here, and then the theta entry for this row, and then the v hat entry for, theta entry for this row, v hat entry for these columns, theta entry for these columns, and then you have the real and real imaginary portions corresponding to the two portions of this function. They are themselves Jacobians, yes, but really I'm saying the Jacobian, this whole thing is just going to be defined like this. Yeah?
You said for C is all real.
Yes.
So for, if you have the Q that represents the reactive or the
Yes.
part is still real?
Yeah, yes, it is. So it's actually interesting here. Maybe I should write this out a little bit more. So what this really is this is saying that G of Z equals, I wrote it now in terms of these sort of complex components here, but what it really is saying is that G of Z equals the real component of, I mean, I'm defining G as a function of Z. So, and you know, V, the complex V is not an element of Z. So what it really is saying it's the real component of, well, it's diag V hat times diag E to the negative, so e to the j theta, Y conjugate, but you'll end up doing sort of the things that has real imaginary components right now, times this same thing, diag V hat E j theta, negative E j theta, minus P plus JQ. So really, when I say this first bit, I mean this. I mean expressing these complex numbers here in terms of the real entries here. But every input to this function is real, and every output is real. It just, some of them denote real or complex components. This will probably be a little more concrete when you do implement it. But yeah, you will implement power flow using these equations on the next problem set.
And S is known, right?
Yeah, well, S is an input. So S is just equal to, sorry, I wrote theta here, JQ. S is just equal to P plus JQ, which is one of the inputs of the function. So all these things are known, but you have to put them in the right form to actually see what they are. The physical meaning of the Jacobians are they're about derivatives. So I mean, they are a matrix of product of element-wise derivatives. So what they're saying is physically, if you change this matrix a little bit, or sorry, this entry a little bit, if you change theta 1 a little bit, the voltage angle a little bit, how will that change G, the output, which in this case is the mismatch between the real power and the, sorry, between the power here computed as it should hold for power flow and the power that you have assigned here. It's sort of interesting here because when you start off with some, so what we're doing, remember, was we're finding a solution to this equation, right? This one here. We're finding a solution to it. And this equation has physical meaning when it holds with equality, right? That's saying that it has to have this by Kirchhoff's voltage and current laws and by Ohm's law, it has to have this. So in cases where you have some input where this does not hold, where this is not equal, that really has no physical meaning, right? That's just saying we just have a bunch of numbers we've assigned. It only really has physical meaning when you have solved this problem. So we're going to use Newton's method to solve the power flow equations, but those really only have physical interpretation when we've actually solved them. In the intervening steps, these are just numbers. And it really doesn't matter until we have computed the solution what those numbers are. So what the Jacobian is physically is sort of weird because the function isn't anything but the power flow mismatch. Now, the Jacobian of this function, when the function is equal to 0, so when we've solved it, we can again compute Jacobians then. Those are, we can do that. Those are not 0. The Jacobian when this function is equal to 0. Those have physical meaning. But in intermediate, and that sort of is, okay, how will our power flow equation change in the first order approximation if we start changing numbers a little bit? That's actually very, very useful to think about for things like perturbation analysis. When you have sort of a solution, you want to know if I change things, if I increase my load, what will happen? Which directions will this go in? That's very, very useful there. But in the case of sort of intermediate steps where you're just solving this thing, these are just numbers. This is just a function. Maybe writing it out this way too makes these terms a little bit more intuitive about why you might get something like that? You can sort of see now, I can take this out, you might get a diag term there like this. If you take this one, or rather if you take this one, you might get some kind of diag term there. If you take this one, you might get some term that looks like this here. You do, in fact, get those terms, but again, that's the important part is just knowing what the equations are. Because it's much easier to write them this way. Compute them this way, by the way. I mean, MATLAB, this is a couple of lines of MATLAB, right? As opposed to, it would take, I mean, you're looping over all the entries here. You're seeing which one's connected, which one's not connected. That would be really, really nasty to compute all these in MATLAB. Whereas this is really simple. It's a couple lines. All right. So, okay. So now, this is all well and good, but I've defined it a little bit strangely, right? Because I defined z as being a 4n input, and this function is having 2n outputs, right? So I've defined this function g from r 4n. Oops, that's not how it goes. r 4n to r 2n. And if we were allowed to change items in this matrix, or the input, kind of as if we wanted, well, of course, there are much more than just one 0 to this function. We would have 4n unknowns and only 2n equations. We can find a lot of different solutions that have g is equal to 0. And that just corresponds to basically every single possible power flow scenario you could have, right? If you can pick all the variables here, then of course you can find lots of solutions to this. That's just every single possible physical power flow. But what we do have in reality is we know 2n of those entries, right? So 2n are fixed. But this formulation actually makes it very easy to account for that without changing much math at all. And all you do is you let I, some subset here, this equals the indices of the unknown entries. So we're going to just set the other entries just be equal to their values, right? We're going to just, we have some initial z, it has all those entries. We're just going to set some of them to be the values that they are. And we're not going to ever change those. Those are effectively, I mean, they are fixed. And we're just going to change the z subscript I entries. And the equation for this is just Newton's method again here. The equation would just be z subscript I. That means all the entries in z that are unknown. And by the way, in MATLAB, this works exactly the same. If you have a vector and I is some set of indices, then zi is just a vector of only those indices. So this is sort of, I'm writing it this way because this is exactly translates into the MATLAB code. We're going to set zi to be equal to zi minus, sorry, I'm confusing my MATLAB and mathematical notation here, zi minus j. Well, we want all rows. I'm kind of actually mixing MATLAB and normal notation here anyway. But we want all rows of j, right? Those are the corresponding to each of the outputs. But we want only the column j that correspond to those unknown entries. Those are, how does this function change when we change those unknown entries? We don't care about how it changes when we change the known entries because we're not going to change those. So we're going to look at only the I entries here. We're going to take this Jacobian and we're going to invert it and multiply it by g. G again is just the same as before. G has only 2n entries. So this now is 2n. This thing here is 2n by 2n. Oops. 2n by 2n. And this thing here is 2n. So all the math, kind of all the matrix multiplication works out here. And by the way, in MATLAB, this is just the same as this. This is just literally zi equals zi minus j all rows I backslash g. So the reason why we do this is that this makes it very easy to set up these equations in kind of a very natural way. We can easily write out kind of our g function here in terms of these entries of these equations. And then we can easily compute Newton's method on the entries that we don't know without having to kind of do any fancy construction of particular indices in a variable or figuring out exactly what is what. Which indices correspond to, without sort of keeping in our minds which indices correspond to which unknown variables. This kind of equation just makes it a lot simpler. Maybe I'll erase this, because these are just the sizes of these things. I guess confuse it. But this is sort of math, and it's just the MATLAB way you do it. Now, a big caveat here is that Newton's method is not guaranteed to find a solution for these problems. First of all, we have nonlinear equations. They may just not have a solution, period. You can pretty easily come up with powers and voltages that you cannot solve physically. What this corresponds to is saying that there's no way these generators at these voltages could actually provide power to these loads, which makes sense, right? I mean, if you just don't have enough power to supply all your loads, it isn't, surprising that, and your slack generator would get to be trying to pump up as much power for everyone else. It's not surprising that you wouldn't be able to find a solution to this. So there are plenty of cases where you cannot find a solution. Even when there does exist a solution, we won't always find it with Newton's method. At least not this typical version here. You might have to, for example, sort of take smaller steps, scale down this step here. Rather than just subtracting this whole thing, you subtract some small portion of it. This is necessary in practice sometimes. But for a lot of cases, this works really well. And it works kind of incredibly well because the Jacobians are sparse. So this isn't even that complex. This is not even that costly an operation to do mathematically. You really are doing actually quite well to solve the inverse of a few sparse matrices. And you can solve systems of tens of thousands of nodes in a few seconds on a computer. Again, when they're nice problems that you can just take these steps, but oftentimes you can just take the full Newton step every iteration, and these converge really, really quickly in a lot of cases. So here, one more note. In practice, there isn't too much relevance to the absolute voltages. I mean, power systems operate on high voltages. There are lots of lines that have 750 kilovolts or so. That's a lot high voltage. You have transformers that step up and down maybe, but we'll think about a fixed voltage. You might have really high voltages, high powers, all this kind of stuff, really high stuff on your big resistances on your network. But typically, you don't really care about the absolute values, right? I mean, yes, if you're worried about knowing the actual voltage for safety reasons, that's fine, but it's easy to scale these things. And making them big just makes the numerics less stable. I mean, you're going to run into more issues of things like overflow and stuff like that, numerical overflow. So typically, we don't actually care about the actual magnitudes of the voltage. We just care about their relative magnitudes. So what is common to do is just specify voltages not in terms of 750 kilovolts or 700 kilovolts, but just in terms of what's called a PU, or a per unit number, which essentially just means that the voltage is scaled to be about 1, on the order of 1. In fact, usually what this means is that the voltage for the slack bus is set to be 1, or set to be some number around 1. And all this is doing is we're just numerically scaling everything. So you scale your resistances too, and your reactances. You scale your powers. You scale everything when you do this. And what you'll see actually in a lot of common test examples for power flow is that people also include, they have a power flow example and they include a base megavolt ampere, which is essentially how all these numbers scale to real numbers, because you scale power and voltage and all these things equally, and so that number just tells you how to scale everything. But the actual numerics are typically solved scaling the voltage around 1. So if you see sort of results of power flow, you'll see things like voltage equals 1 pu or 1.1 pu, and that's just indicating that. And this is just how we're going to scale it. So quick chance to show what this actually looks like. So here is a simple 3-bus example. Okay? So we have our slack generator. That has a voltage of 1 pu at 0 degree voltage angle. And those are just both references, so we just set those. The PV generator, let's keep the voltage magnitude to also be 1. That we can set, remember. Let's generate 0.5. Again, this is scaled too by that base megavolt amperes, but 0.5 watts, or 0.5 times x watts. We know the resistances and reactances of each of the lines here. And we know for the load what the real and reactive power are. It's just a simple example, fully connected network here even, so there is no sparsity here even. But it's supposed to have these things. And what you get is this, is the power flow solutions. Remember, power flow solutions give you, at each node, complex voltage and complex power. So the complex power here, complex voltage is what we had before. Complex power, well, it has the numbers. This one produces 1.17 watts or whatever watts of real power and this much reactive power. This ends up producing the amount of real power we specified, right? Plus, with a voltage angle of -2 degrees, and this amount of reactive power. So remember, here, this was known. We solved this from our equation. This is a slack generator. This is a PV generator. We specified this and that, and we figured out these two things numerically. And this is a PQ load. We specified this and figured out these numerically. We can also now go back and actually compute currents, right? It's from Ohm's law. Just this voltage minus that voltage divided by the resistance of the line, which we know, or the impedance of the line, which we know, gives us the complex voltage flowing over this line. Sorry, complex current flowing over this line. And one thing to kind of note is, as a general rule, current will flow, which makes sense, of course. Current will flow from higher voltage to lower voltage. And that just makes sense, right? Ohm's law says the voltage difference over the resistance, if it only had resistance, that would be the current flowing through it. Similarly, it typically flows from higher voltage angle to lower voltage angle. That also just follows from Ohm's law when you were if you were only to include reactance in there. We're not gonna don't worry about sort of when, well, actually do think about it, but when there's both, you know, if there was a case where one was higher than the other and the other was lower, then there would be kind of there'd be this trade-off, of course. But typically, in general, you will find the solution and then current will flow in these directions from higher voltage. So these voltages are the same, for example, but current is flowing because the voltage angle is lower here. So current can flow for either of those two reasons, right? It can flow either from different voltages or from different phase angles. And just to sort of show how great Newton's method is, we'll finish up with this today. here is a plot of the residual g. That's the absolute, the 2 norm of g. So we want g is our function here. We're trying to make it equal to 0. This is a plot of how this 2 norm of g evolves per iteration of Newton's method. So this is our 3-bus example here. And after 6 iterations, g is equal to 10 to the negative 15. That's numerical precision. You can't get closer than that on a computer. I mean, on a computer with using double precision arithmetic. So 6 iterations and it solves it. I mean, that sounds great, but it's also a 3-bus example. It's pretty simple, right? So here's another example, which is a 300-bus example, an IEEE power test case, which will the ones you'll actually use in your homework. These are kind of the standard examples people use when they study power flow. And the cool thing is it still takes 6 iterations. I mean, it could be a little bit more, but we don't quite get the same thing. Maybe we don't want to do one more iteration to get to exactly numerical precision. But 10 to the negative 12, it's already pretty good. You can't really complain about that. Now, if you and remember, this is a log scale I'm showing you here, and a linear scale here. And it is converging even faster than a linear line on this graph. That's really, really fast convergence. It basically means that every time you're getting, this is called quadratic convergence, sort of formally. But what it means is that this graph, you have a thing that looks like quadratic even on a linear and logarithmic graph, which basically means you're going to converge really, really quickly. So effectively, for a lot of cases, when you can solve this, when this converges, it typically converges really, really fast. So it's not a case of doing 100 iterations, maybe you get kind of close. This is a case of you will do 10 iterations and you will be at the solution to numerical precision. So we are actually solving this as well as we can on a computer. Again, using double arithmetic. You could use arbitrary precision if you wanted to, but let's just stick with the, it doesn't really matter the 12th decimal place to us. So that's the nice thing with this method here. There have been a lot of other ways of solving power flow. People have proposed as approximations to this that typically work a little bit slower than Newton's method. They essentially allow you to simplify some of the computations here, or maybe not actually compute this inverse here, but just sort of multiply by the Jacobian, things like this. But for cases where this converges, this is a really fast and efficient method, and kind of has become the most standard way of solving these problems. So you will all implement this on the next homework. You kind of look forward to that. But it isn't that bad. It's 15 lines of MATLAB code, and you've written a power flow solver. OK, so what we're going to talk about next time is actually a simplification of this power flow that tries to get us, even though we can do this, nonlinear equations still are kind of nasty. And we get back to linear equations, and we can, by making enough approximations, we can. And that's the method called DC power flow. Actually, I won't mention that at all. DC power flow is a horrible name for it because it's not anything to do with DC circuits or DC current. I guess just direct current. It is just a name people give to an approximate AC power flow. Which is, so just keep that in mind. And I guess the other thing, yeah, there's lots of extensions to this are possible, things like fast coupled power flow. They also do things like use conjugate gradient methods to solve this instead of actual inversion here, if you know if you've heard of that before. It's not guaranteed to exist. There can be situations where, like I said, you can't solve this, so there's no way, there's no physical realization of the system, so you're definitely not going to solve it. And there are cases where it does exist, but there may be more than one solution. You can actually have these cases from power flow, from the nonlinear equation. So all of these sort of niceties, I mean, all these sort of annoyances do motivate the need to go for a simpler, maybe approximate version. But in a lot of cases, solving these methods is really, really fast. And this is not a lot of computation to get here. So in a lot of cases, it's very, very easy to just go ahead and solve this. Pick up next time, as I said, with this approximate power flow, and then we'll also pick up with optimal power flow, which is these things in optimization problems.